So we are back and we are in SketchUp right here. And what is this mess that you're looking at right here? Well, this is the soccer ball Earth, everybody. And so without anybody even challenging us on us calling Earth's coordinate system a football, it's time for us to go ahead and explain this for y'all. We're going to get out ahead of this, and what's going to happen is somebody's going to come along and wake up and realize that this right here the 2D coordinate system projected to scale is an onion looking thing like this. It's really nice. And then we were showing people how it projects to a football. Now what we have done is to make this football, we made all these lines of longitude here equal distant. So from the equator to 10 degrees, from 10 degrees to 20 degrees, from 20 to 30, so on, so forth. Each one of these are equidistant because that is what the coordinate system says. Right? Now, a savvy globe earther will come along and say, well, the 600 nautical miles isn't up the center of this. It's actually going around the outside of it. And so let's show you what that actually looks like. And to do that, I want to show you all that what this is all coming from is the Andrew Marsh. What I did is I went through and took a whole bunch of screenshots based on a day, just like this. So it's Equinox, and I've got it at a solar noon. I've got everything zeroed. So we're at the prime meridian, and we're at the equator. All right, 0 and 0. So all the images you're going to see in the graphics that I'm presenting are based on this day, this type of a setup. And I've got north on the left-hand side over here. So we are in the west looking east at this view right here. And I want to show everybody that it goes from 90 degrees. All right, this is the South Pole right here. And here's, passing through the 40s. Here we're getting up to the equator. All right, we're at latitude 0. The sun is 90 degrees straight up. And then we're going to the north. And this is the tilt until we get to the North Pole, and it's flat again like this. And so we've got the sun right at the horizon, and the North Pole and the South Pole, right, all on a plane. I just want to point that all out, and then we're going to start taking a look at this SketchUp that I built here. And so let's go ahead and zoom in at our North Pole. And you're going to see that what I just showed you, here we're at the North Pole, the sun is at the horizon. And then as we work our way around, here's 10 degrees or 80 degrees. Yeah, it's 10 degrees of between these two places, but this is considered 80 degrees north.
Latitudes.
Yep, latitudes. Here is 70 degrees north latitude. Here is 60. Here is 50. Here is 40. Here is 30. Here is 20. Here is 10. And here is the equator. Right? So what they want you to believe is that the latitude and longitude coordinate system, that the distance between the 10 this 10 degrees, 20, 30, 40, 50, 60, 70, and 80, that it's not equal spacing. All right, it's not equal spacing because they're saying that you're looking at the distance, right? That these are all equal. So each one of these dotted lines I have coming out here are 10 degrees. So here's the 10 degrees. That's the reason why I drew this 10 degree latitude across here to this point. This line is where the 20 degrees intersects. All right, so when you do that and you take an orthographic look at Earth, you will see that these outside skin distances are equal distant. These are all 10 degrees from each other, but then that makes your latitudes appear to actually get narrower from the equator as you get up here, because this is supposed to be part of a ball. It's supposed to be here's supposed to be your equal distant out here, and then the lines of latitude are getting closer together. All right, so I just helped explain this for the heliocentrists, and then they go tilting around underneath here, so that this is 10 degrees south, this is 20, this is 30, 40, 50, 60, 70, 80, and 90, and you're upside down. So you won't find too many heliocentrists that have put together a graphic so so detailed with so much information regarding what is supposedly their model. Because now what we're going to do is prove that this idea that you're going around an outside edge that's equal distant here, and that you're on a ball, be it a football or a soccer ball, it's got a really huge flaw in it. Because what's happening is there's a baseline that's being adjusted by 10 degrees every 10 degrees. So when we go from buildings being perpendicular at the North Pole right here, when we go to 80 degrees north, this 10 degrees difference right here means that this baseline, which is going to be your tangent drawn to a center of a radius Earth, that this tangent is different by 10 degrees. So this baseline has changed by 10 degrees here. It's changed by 10 degrees here. It's changed by 10 degrees here, 10 degrees here, 10 degrees here. This is the baseline changing until we get around to the equator. And what you have at the equator is, because 90 degrees have added up, you've added an extra 10 degrees to your baseline. You're now sideways. All right, so you literally have to be sideways here. And then if you continue adding the 10 degrees extra to each one of these baselines all the way around, you get to the point where you're completely 180 degrees upside down from where you started. Right? So the real system, if we go to Andrew Marsh, you'll see that there's only 180 degrees. If we go from 90 degrees south here and we go to 90 degrees north right here, that's a total of 180 degrees. But you'll see at no point did these buildings go upside down. Right? You notice that the buildings did not go upside down. So let's go back to what they have right here, and notice that so each one of these, you'll see it looks like they're all lined up. Each one of these would be pointing. You've seen all these heliocentric diagrams before, where each one of these are pointed to what would be a sun 93 million miles away out here. All right, and then it's 864,000 miles in diameter, which actually makes it to about a half a degree of our sky, which is acceptable. That is about a half a degree. But the distance and the scale is a major problem, because you can't even model that, right? It's literally impossible to model that in any way. Where I want to point out to people, I'm going to see if I can find this. Let's see here. I have it open. If Earth was a pixel, what size screen would you need? All right, so if Earth was a single pixel, to see the sun as a visible dot on the same screen, you would need a screen roughly 109 times larger than a standard screen. So they're saying that to have this is not the answer that I had before. I want that one. This one from Quora. This one does the whole solar system. I want to point this out here. All right. So if Earth is depicted as one pixel on a screen, how must the screen be able to show the entire known universe? Well, they're just going to do the Milky Way galaxy in this calculation. So the average pixel size in millimeters is 0.2645. The diameter of Earth is 12,742 kilometers per Google. The diameter of the Milky Way galaxy is 100,000 light years per Google. 1 light year is the 9.46 times 10 to 12 kilometers more Google. So the Milky Way galaxy is this. Thus, if Earth were 1 pixel, that equated to 12,742 kilometers. So 1 pixel is representing Earth, then the Milky Way would equal 74. What is that?
Quintillion? Where are we at? Sextillion?
Yeah, it's quad. So this is the millions, billions, or 74 trillion pixels wide. And so multiply that by the width of a pixel, and you get this number, which is like 19 trillion. So toss some unit conversions, and that turns out to be 19,643,000 kilometers.
Wow. Compared to 1 pixel?
Yeah, if Earth
That's not resolvable. That's unresolvable.
If Earth was 1 pixel, then the screen that you would need to be able to show Milky Way to scale is
wow.
Yeah, 19 million kilometers, almost 20 million kilometers.
That's crazy.
The width of your screen would have to be to have Earth be 1 pixel. So wow. The thing is when you get into the idea that you've got a 93 million mile away sun that's 864,000, you've never seen that ever in your life. There's no possible way of representing that. Like, you cannot put the sun, moon, and Earth into a 3D model and show it. All right, there's other links that there's no computer monitor, TV monitor, like there is no screen big enough to actually even represent that. So it's not real. It's never happened. You've never seen it. The only way that can exist is in your imagination, right? Because they've never shown you a single scaled representation of it, and there is no program, no computer that can. It's just not possible. So this idea that all these things are lining up to this fixed sun that's way out here 93 million miles away, and that each one of these circles of sight are going around a curve like this.
While Earth is spinning. Let's go back to this.
And I want to show you again that because we're on a fixed and stationary plane, in order for this to be the heliocentric model. So this is one of the things they keep on saying, oh, this is based on the globe. This is based on the globe. No, it's not, because here we have the sun right here. We're at the equator, and then we have a fixed plane like this. But if this was the globe model, this plane would have to be tilted sideways. The plane would have to be tilted sideways right here in order for the sun to be straight out here. Just wanna go back to this. The plane would have to be rotating. If we're at the North Pole, or at the North Pole, everything's right side up like this, then in this 180 degrees right here, this yellow ring should not be rotating at all. The plane itself would have to be rotating, where once we get to the South Pole, now all of a sudden these buildings are upside down. Right? See, we had the full 180 degrees right here, but all on a fixed plane that didn't go upside down. If this was the globe model, this plane would have to have flipped and gone upside down. At the equator, the model would have to have the buildings sideways. And keep in mind that in that fixed and stationary model, that all of this would have to be rotating. The sun stays still, and then this whole plane that's right here has to be rotating to give you the time of day. See, everything in this model has the sun moving around the observer on a fixed and stationary plane. It doesn't have a sun stationary out here that the plane itself rotates. Right? The plane does not change pitch as we go from one latitude to the other, and that's what it would have to do to represent heliocentrism. So you can't have the all these lined up out here to a fixed and stationary sun without actually having the plane rotating. You follow that, brother?
Absolutely. I completely understand how it works. And it's easy to see. People should very easily be able to understand it. But continue.
All right. And so now I want to do is show how this really works. So here's the 2D onion, and we're going to have those same circles of sight at all these different latitudes. But I want to point out here that, so here with the 2D onion projection, each one of these distances, we're at the equator. So here's the 10 degrees north. This is equidistant here. 10 to 20, equidistant. 30 to 40, equidistant. Each one of these are equidistant to the north and to the south. Right. So now if we come in and take a look at this, this is what we are saying is taking place. We're with the Andrew Marsh. We're at the North Pole here, and sun's down here at the horizon. Here we're at 80 degrees north here, and the tilt is like this. Here's 70, here's 60, 50, 40, 30, 20, 10, and the equator. Right? And then heading south, we've got 10 degrees south, 20 degrees south, 30 south, 40, 50, 60, 70, 80, and 90, where the sun is back at the horizon like this. So on a flat plane, we've got all the latitudes. We're at the prime meridian. We're at the center here, and we're showing how there's only a total of 180 degrees of rotation, and it's all on a fixed and stationary plane like this. The model that we're using, you can see that the baseline has never changed. The baseline remains the same, and just the tilt of the sun is changed by a person's latitude here. There's a full 180 degrees right there. But what the Globers want you to believe is that that every 10 degrees, the baseline changes without you ever being given a measurement saying that, okay, you've gone 10 degrees, now you need to adjust your baseline. Right? This is just all absolutely assumed that the baseline's changing, that once you've gone halfway around like this, that you're 90 degrees out, and once you get around here, you're a full 180 degrees out, upside down. Whereas on the On the 2D version of it, it's just tilted like this. This is all the same day. So we're going to continue to be showing everybody how the seasons work. This is just a day on the equinox. This is the 2D onion projection where everything is equidistant between its lines of latitude. And this is the one that if you were to project this three-dimensionally, it turns up looking like a football. So when you take that 2D onion and everything is equidistant, this is how you get your football Earth. That's based on each one of these actually continuing to remain equidistant from each other, like it does on the two-dimensional plane, right? So reason why we went with the football is because this is the way we measure Earth. We measure it flat, and if you want to keep it equidistant, it's not the skin on the outside of a soccer ball. When you go 600 nautical miles to the north or 600 nautical miles to the south, that's done on a plane. So when you wrap this up, this is how you end up with football Earth, American football Earth, right?
Yeah, that's it.
Yeah, so just wanted to get out ahead of that, show everybody how this works. It's going to be, part of our presentations going forward. Just continuing, this is how you explain the seasons, and then also how you travel. So another thing I wanted to show people quick is that when we use here it is. When we use this moleweed projection, which is really close to the onion, the advantage that this has right here is the ability to move it, to recenter things around. And so this right here is now centered to the equator and the prime meridian. And while not perfectly an onion, it's close enough for a person to sort of get and understand it. So what you see out here is that the coordinate system at the equator is absolutely dead on accurate, because this is equidistant. You have equal spacing of from the 90 to 80,
latitudes.
70 of, yeah. So these are all equally spaced. That's wonderful. We love that. But what happens is when you start looking at these longitudes out here, they're very distorted, right? Even though this is like a 2-scale projection of Earth. So the only place that this is accurate is to what longitude you're centered at. So if I turn it like this, right, then now all of a sudden this line is accurate from top to bottom. but nothing else out here is. If I turn it like this top to bottom is accurate, but nothing else out here is. So I created a little mask here to show everybody that if you want to travel around Earth, that you can everywhere that you want to look, like the coordinate system actually has to move like this in order to give you a correct representation. And you don't bother looking anywhere outside of this section right here. You can see that the lengths of the latitudes and longitudes are being drawn correctly here. So this is when it comes to people asking about the borders, how the borders work with the stereographic virtual reality. This is the only way that you can represent the lats and longitudes correctly. So anywhere you're at within this narrow strip right here is being represented to scale. You'll see that once we go across the international date line here, that all of a sudden there's going to be a big rewind. We'll start over right here. But yeah, so as far as looping or anything like that's concerned, this totally shows how that's not real. All right, the only way you can draw the coordinate system correctly and to scale is like this, and it has to be centered to your longitude, because you can see that even though the coordinate system is to scale, it's not able to accurately project it once you get out and away from what it's centered on.
Yeah, so let's do the fun experiment that everybody always wants to see and everyone always wants to ask, is the trip to Antarctica and then up the backside of what would be the Earth if it was a sphere. We're going to actually show you the way that actually works in reality. Jason's going to show you here. This is, everybody pay attention. Let's take it back to let's set the prime meridian on Texas, where you basically have it, the center point. And everyone, I'd really like you to pay attention. So we're now going to travel. We're going to go to Antarctica, and then we're going to travel back up the backside, because people are going to ask, where's the backside of Earth here in your model, right? Supposedly Earth has a backside. Well, pay attention, Jason. Take it away.
Yeah, so 90 degrees west is where New Orleans is right here. And so this is nice center, because so here's when we're centered to the prime meridian being 0. And then here's your 90 west. And so this all really lines up here where we're going down through. If I turn this mask on right here, let's see, I need to get your camera up one layer. All right, that's better. And so coming from Texas, we're following basically this straight north-south pass, because right here is your 80 degrees south, and this is pretty close to, I think it was like 82 degrees west. So this is an absolutely to-scale representation of what the flight from Texas to Union Glacier would be if we just went due south. All right, so once you're at Union Glacier and you wanted to continue to the South Pole, you would get down to the South Pole right here, and then what we need to do is spin Earth over to 90 degrees east. And so you would be coming up from the South Pole here, up 90 degrees east, and you'd be coming in here by Bangladesh, in between India and Thailand, in this area.
So there's no shortcuts. It's basic. You would travel to Antarctica from the 90 west, how Jason showed it. You'd fly due south, you'd get there, and then you'd set your coordinate to that longitude. Then you'd start traveling up your latitudes north, and you'd come up and you'd get to Bangladesh. And if you kept headed north, you'd end up getting to the North Pole. And then you could then travel back down to whatever latitude you choose once you're at the North Pole, and you'd be able to start all over again. This is the big gotcha that Will Doofus tried to have, and all these other people. And it's, you know, it's so easy for someone to, you know, throw crap at the screen. You know, people that got no names, no faces, they've never done any modeling, they don't do anything. They come here and they think they can pick apart something, or like Will Doofus, who didn't do any work, has never done any modeling, he doesn't have any idea. He's never even once questioned the fact that he lives on a spinning sphere, ever. But yet he'll come and throw crap at the screen instead of actually looking. And all it takes is some dedication and some patience and some research into the systems, the coordinates, into the ways that we view our reality, and you'll be able to see what Jason just showed. Again, so if you want to know how you travel where the supposed backside of the Earth is, Jason just showed it. And there is no backside. Again, all this is being rendered to an observer. The largest field of view that we have, right, is roughly from the sky between 50 and 80 miles. Now, the largest distance sighted was from Kathmandu to Mount Everest, right? From the ground, you can see Mount Everest. But up in the air, everything, it washes out, it pixelates out. We only have such a small area. That's why there's no pictures of a sphere or of a complete flat plane, because you're in a stereographic virtual biblical reality.